plus 1 minus 1 on top.
Yeah, but what I noticed I did wrong though, after I watched the video, was that I didn't multiply both things by 2. Let's do 2x minus 6.
You don't have to.
Yeah, he showed it in the video.
I mean, you're going to get, if you do the dx, you're going to have dx divided by 2.
Yeah,
so
so
really
I
you
got
can bring the 1 half down.
I got this number wrong, and then I did partial fractions here to get that. And then once I did that, I wasn't sure if I was able to establish part-hand squared.
All right, let's get started. I'm not. You want me? Do you want me to today? All right, everyone, let's get going here. We're gonna continue in 6.6, the improper integrals, but I wanted to entertain any questions you might have over the homework, only on 6.6. So I won't take any questions on partial fractions, but if there's anything on 6.6 you want to talk about, any of the problems?
22. I saw the correction you did on the solution, but I don't know exactly how you did the continuity.
I did a solution.
After you get this part, I don't know how you use the limit, how you got 0.
Okay, let me work through it because this problem's a good problem. All right, so the integral goes from 0 to infinity of e to the x over e to the 2x plus 3 dx. This is number 22 off of your homework. So the first thing we need to do is figure out what the antiderivative is. So you might want to work on that by itself without all the limits of integration up there. And the key to doing the problem is to realize that e to the 2x is the same as e to the x squared and then plus 3 dx. Right? E to the 2x is the same as e to the x squared. So in doing that, you kind of already see, hopefully, that if you let u be e to the x, the derivative of that, derivative of e to the x is itself, dx. And you have e to the x dx in the numerator. And then your u is going to be this e to the x. I know that's not your question, but okay. Anyone have any questions on that, though? It may take you 20, 30 minutes, an hour to figure that out, but that's what happens. Hopefully not that long. So in the numerator, I'm just going to have the du on the outside. That's my yellow part. And then 1 over e to the x, which is u, squared plus 3. And that will go straight into the formula for arctan, with a being what? Square root of 3. So this equals 1 over a arctangent of u over a, right? But u in this problem is e to the x, so I'm just going to go ahead and put it here now. E to the x over a, and then plus our constant. So that's the antiderivative. Now I come back to the integral. This equals 1 over root 3 arctangent e to the x over root 3 evaluated at infinity and 0. So here's what we have to plug in infinity, figure out what we get, plug in 0, see what we get, right? So let's go ahead and do that. Let's plug infinity in first. Say this equals two things, something minus something else. So when we plug in infinity, it's 1 over root 3 arctangent of... Now, what is e raised to the infinity? Again, that's what's happening to the e to the x function as you go to infinity. Where is it going? Infinity. So that's basically infinity over the square root of 3, which is still infinity. So in here I have infinity. I'm putting in red just to stress to you, infinity, remember, was the idea, not a number. On the other part, let's plug in 0. 1 over root 3 arctangent of, now plug in 0 for x. So what's e to the 0? 1. And 1 over root 3 is just 1 over root 3. So that's going to turn out to be some number, which we'll figure out in a second. We still need to figure out what's happening here. So when you say inverse tangent of infinity, what the hell does that mean? Here's the way I would look at it. Remember that the inverse trig functions are basically the reverse of the trig function itself. So if you have inverse tangent or arctangent, that's the inverse function of tangent. So I'm going to graph tangent. Right, I'm going to graph the tangent function. Here's what tangent looks like. Tangent does this. Right, that's tangent, not inverse tangent. That's tangent of x. So when you say, this part over here, when you're saying, hey, what's the inverse tangent of infinity? You're saying on the tangent function, what makes it go to positive infinity? What value makes the tangent function go to positive infinity? Do you know where that asymptote is? That dotted line, where is it? It's at pi over 2. This happens at pi over 2, right? If you try and go towards pi over 2, your tangent function goes to infinity. Does that kind of make sense? So let me write that down next to this, just so you can really see what I'm saying. Tangent of pi over 2 equals infinity. Now look, the math gods are rumbling and, upset with me because this is not true. Tangent of pi over 2 is undefined. But as I approach pi over 2, I'm going towards infinity, right? So if I take the inverse tangent on both sides, what happens on the left side? Tangent, tangent inverse, cancel. You just get pi over 2. So that means that tangent inverse of infinity is pi over 2. But this is all within like the idea of a limit. It's not hard numbers here. Does that kind of make sense? So tangent inverse of infinity is going to be pi over 2. It's, well, you can actually look it up. It's probably on your, is it on the sheets? It's not one of the common functions. It looks like this. Pi over 2, negative pi over 2. It's like this. Yeah, it's like that. Roughly. Remember that inverse functions are reflections over the identity. So you would have to take the identity function and then mirror it. Yeah. Yep. All inverse functions are reflections over the identity. So if you knew what arctangent looked like, because this is the graph of arctangent right here. If you knew what arctangent looked like, if you just knew it in your head, then you would know that as you went to infinity, what's it headed towards? Pi over 2. And you wouldn't need all this other stuff. But not many people know what the arctangent function looks like, or arcsine, or they may have trouble with those. So it's easier to go backwards from the function that most people know. That's my opinion. That's my experience of it. Any questions on that, though? That's absolutely a skill you're going to have to be able to demonstrate on the test. To have something like inverse tangent infinity and be able to go backwards to pi over 2 from that. Yeah. When? I don't even know when the test is. Yeah. I haven't looked. We have a lot of information before our next test. I may move it. It's going to take place when we finish up chapter 7. Or at least 7:2. All right. So now I can come back up to this problem. This is now 1 over root 3 times what? Pi over 2 minus 1 over root 3 tangent inverse of, I'm going to say root 3 over 3. All I did was rationalize that. Now, is that the answer in the back? Or did they actually figure out what arctangent is? I did this in my solutions, right? So I went further than this? Pi over what? Pi over 6, yeah. So we have to figure out what this is now. That one's a little tough. The way you'd get that, though, is to know the unit circle real well. And if you go out to pi over 6, the coordinates here are root 3 over 2, 1/2. And so at pi over 6, what's tangent of pi over 6? It's the y coordinate divided by the x coordinate. Agreed? And that's just, when you flip and cancel, you get 1 over root 3. So that means tangent of pi over 6 is equal to 1 over root 3, which is the same as root 3 over 3. Right? Now take arctangent on both sides again. Arctangent of tangent is going to give you what? On the left side, just pi over 6, and then on the right side, you have arctangent of root 3 over 3. So that piece up there is going to be replaced by pi over 6. Now, your calculator should give you an answer. If you did arctangent of square root of 3 over 3 and you're in radian mode, it should give you pi over 6, but you probably won't know it's pi over 6 unless it's TI-89 or something. Because TI-89 will say pi, the symbol pi, over 6. If not, it'll be a decimal. Question?
I didn't know that it was going to be pi over 6. What could I do to kind of get in that direction?
Well, the most you'd be able to do is on your calculator do it and get a decimal. But then you're going to need to turn everything into decimal and give me a decimal answer. But all the problems that you'd ever be faced with, that number that we had in there, whoa. Oh, man. The number in here is going to be something off the unit circle, most likely. On a test, I would never give you something odd that would be an angle that you wouldn't be able to recover off the unit circle. I mean, like, here's one that would possibly come up. Arctangent of 1 would be what? Pi over 4. Because then you're looking on the unit circle and you're saying, where is the y and x coordinates, the ratio 1? Where are they the same? Or it's going to involve a root 3 or something like that. It'll be off one of the common angles. Okay, so then you put this together. I don't know, have I answered your question yet? Or yes, we're there. So this becomes a pi over 6, and now you put them together and you're there. Okay? Other questions over homework?
17, I ended up being ln squared.
Number 17. Okay, let's take a look. Integral 1 to infinity ln x over x dx. So this is a basic substitution because I see something in its derivative. I see natural log of x. The derivative of it is 1 over x. So there's a 1 over x there, right? So my u would be natural log x. Du would be 1 over x dx. So this should just turn out to be natural log x, 1/2, right? 1/2 natural log x squared. Evaluated from 1 to infinity. So I'm not showing you how I got the antiderivative. That's just it. Is that all right, or okay? I'm not going to work it out, but that's what I did. Okay. Now, plug in. So, do you have your question yet, or no? The square between the ln. Oh, you just put it like ln and the little square. It means the same thing. Yeah, but that's a different. You usually don't use that notation for powers on logs. You do it for trig functions. It's weird. It just doesn't make any sense. But so plug in infinity, right? First, you get natural log. 1/2 natural log of, here we go, infinity. This is an idea here. Infinity and then squared. And then back here, we're going to have 1/2 natural log of 1 squared. So let's look at the natural log of infinity. You're saying to yourself, what is the natural log doing as you go out to infinity? It goes to infinity, doesn't it? So that becomes infinite. So this infinity squared is infinity, and 1/2 of that is infinity. So this whole thing is becoming infinite. Then minus, over here, natural log of 1, 0, squared is 0, 1/2 of 0 is 0, so that's 0. So you get infinity minus 0, which is infinite. Which means that this integral does what? Or diverges. No, they don't put infinity, they put diverges. Yeah. Any others? Yes. Diverges, yes. Yeah. It's not like I'm going to count it all wrong. If you get infinity, but you forget to say diverges,
Is it only divergence?
No. You can have divergence without it being infinite. And that would be if the limit just doesn't exist. An example of divergence would be this. An example of divergence which doesn't go to infinity would be this. What's the integral from, let's say, 0 to infinity of cosine x dx? Well, the antiderivative of cosine is what? Sine. And now I'm going to go from 0 to infinity. If I plug in infinity, I get sine of infinity, right? And then minus sine of 0. Sine of 0 is 0. Sine of infinity really means the limit as x goes to infinity of sine of x. So this right here, remember, I said last class, I'm really doing limit x goes to infinity of sine x. And that means you're looking back in Cal 1, what does the sine function do as you go to infinity? It oscillates, so it's not headed to one place, right? So this limit right here doesn't go to infinity. This limit right here does not exist. And because the limit does not exist, this is divergent. So you know what I'm saying? If it goes to infinity, it's divergent. But if it doesn't go, it could still diverge. Yeah, sine would be the same thing. One thing I will point out, on this integral we had up here, okay, we got infinity right here, didn't we? If you get that first piece and you see it goes to infinity, right? You see, infinity. You may think, oh, divergent, I'm done. you must figure out what the other part is over here. Because what if it was infinity minus infinity? That's an indeterminate form, and that's going to require more work. L'Hopital's rule, something like that. So if any time you're working these out on these improper integrals, don't just think, as soon as I see infinity, I'm done. Because it could be a little bit more involved than that. So just work everything out. Make sense what I'm saying? All right. Any others? Go ahead. What's that? 19? So partial fraction, all right? Is that what you did? All right, x squared plus x dx. So I'm not going to do the partial fraction part of this, but that's what you would do, right? You would 1 to infinity. Let's see. You would factor this first, x, and then x plus 1 dx. And then you say, oh, okay, with that, I can do a over x, b over x plus 1, right? And then figure out what a and b are. This would turn into two integrals. Anybody have them? So 1 over x. 1 over x plus 1. Yeah, that's right. Okay? Putting the minus in the middle instead of a plus and negative 1 on top. And now you can find the antiderivative of each of those, which would be natural log of x minus natural log of x plus 1. Now, this has come up with a few students who have come to see me. Like sometimes in the book they put the absolute value on the antiderivative and sometimes they don't, right? Here's the deal. If you want to be safe, just put absolute value all the time. The reason that there would not be absolute values in this problem is because your interval is 1 to infinity, and if I plug in any number between 1 and infinity into natural log, it's defined. The absolute value is there in case you're trying to plug something that's negative into a natural log. You can't, so you put the absolute value. Over there, same thing, x plus 1, in that interval, it's positive, so you don't worry about it. There's some in the book when you were doing partial fractions where it was like natural log and inside was a quadratic, and it wouldn't have the absolute value. That's because that quadratic function inside, if you look at it as a parabola, is always above the x-axis, which means it's always positive. So the book and the solution manual, the solutions take that into account. Just keep that in mind. I don't want you to be confused, like, when do I use it, when do I not? Just, that's what's happening. All right, now I need to evaluate 1 to infinity. So let's plug in infinity first. I get natural log of infinity, right? Minus natural log of infinity. And then minus, plug in 1, natural log of 1 minus natural log of 2. Ah, perfect example. I'm glad you asked this question. Because what is natural log of infinity? Infinity minus infinity. This is not divergent until I confirm it is or not. This right here is not enough for me to know that. With me? Now that over there, natural log of 1 is 0, and natural log of 2 is the natural log of 2. So what I'm going to have to do is kind of rethink this and try and figure out if I can resolve this issue. To do that, I need to look at this. I'm doing it in red because this is kind of a separate little scratch work problem. I'm trying to figure out what this limit is. And I know I'm getting infinity minus infinity, right? But how can I resolve that? L'Hopital? Not yet, though. Can't factor. Property of logs that says that if you have natural log of, let's say, u minus natural log of v, that's equal to natural log of u over v. That's a property of logs. And so what I can do here is look at this x as being u and this x plus 1 as being v, and then rewrite this as natural log of x over x plus 1. Now let x go to infinity, And what you get is inside here, infinity divided by infinity. And anytime you have infinity over infinity, you can apply L'Hopital's rule. Even inside the natural log. That's one thing to remember about the natural log. And basically any trig function, you can always pass a limit through that function. So if we want to know what the limit of the natural log of something is, you can actually look at the natural log of the limit of what's inside. So I'm going to go inside here. I'm going to do L'Hopital's rule. This becomes limit x goes to infinity of natural log of the derivative of top and bottom. 1 over 1. And natural log of 1 is 0. So this is just 0. So that means that the infinity minus infinity turned out to be 0. It's not always that way. Okay, in Calculus 1, hopefully you saw that. The infinity minus infinity means that the two functions were fighting each other. It's like a tug of war. Who wins? Who wins? In this case, they compromise. They meet in the middle of 0. Sometimes one function is going to infinity much faster than the other one, and it wins. So that's 0. So all this work right here was just to figure out that question mark of what infinity minus infinity was going to be. So I'll continue my answer up here. This equals, that first part is 0, and then I have minus minus, right? This natural log of 1 canceled. So minus minus, so plus natural log 2. So the answer is natural log 2. Good? Answer the question? Who asked? I'm glad you asked that question because that's what I was just trying to illustrate a second ago. If you have infinity minus infinity, you don't want to be like, infinity, done, divergent. Here, this doesn't diverge. It goes natural log 2. And it went to 0? See, if on a test you put infinity minus infinity equals 0 without any explanation as to why, you'd lose points. Because you would have gotten lucky on that problem. Yes?
So it means that is a fraction, like ln x over x plus 1.
That's what we did over here.
Okay.
But you could have done it in the very beginning.
Okay.
You like at this step right here, you could have, if you wanted to, switched it over to this, and then did your 1 and infinity here. And then as you put infinity in, you'd get your infinity over infinity here. You'd still have to do L'Hopital's rule, but it would just, you just see it earlier, that's all. All right, that's good. Let's move into some new stuff. The same section, okay? What we've done so far and what you did over homework, the idea was that your limits of integration could be infinite, right? Your limits of integration. So we could have integrals that look like this. I go from a to infinity. I could go from negative infinity to a. I could go from negative infinity to infinity. All right, those were the 3 new types of integrals that we looked at from last class. These are known, the book refers to these as type 1 integrals. And they're called infinite limits. Infinite intervals. The idea being that instead of being on the interval AB, the interval is infinite, right? It goes in one direction forever, or the other direction forever, or in both directions forever. So that's the first type of improper integral, where we get this infinity involved. The second type of integral is called a type 2. And let me see here. It's described as being discontinuous integrands. I cannot give you a general picture of what it is with the integral sign because it has nothing to do with the outside, with the limits on the outside, like where you're going from, the interval. It has to do with what's inside. So I'm going to illustrate it with an example. Let's say we have the integral from 0 to 2 of 1 over x minus 1 dx. Your gut instinct on this should be, yes, I know how to find the antiderivative of that, right? That should be like, yes, I'm going to be okay with that. And that's fine. The problem is that something is happening between 0 and 2 when you look at this function, right? What number can you not plug into this function? 1, right? It's discontinuous at 1. You actually have an undefined point in there, don't you? And 1 is between 0 and 2. And so how are you going to find the area under this graph if you have a discontinuity inside the integrand? Do you see the difference? Now, maybe a graph will help. If we just take a look at what this graph looks like. Let me see what kind of graphing I've got ready to go here. What was this? 1 over x minus 1. X comma negative 1 comma 8. There's the graph. What the hell? You know what? We don't have time for this. That's good enough. Wolfram, or not Wolfram, Mathematica draws in the asymptotes. I can have it take it out, but this vertical line isn't part of the graph. So the graph goes like this, and it goes like that. Discontinuous is where you're anywhere where your function would be undefined. And this function is undefined at 1. Now, if you go back into Cal 1, there are different types of discontinuities. There's jump discontinuities, and there's, you've got a hole, so you have what we call removable discontinuity. For us, it's anywhere, if we look in that interval, we are going from 0 to 2. If any number between 0 and 2 causes our function to not know what to do, then we have a discontinuity. So I'm trying to find the area, right? From 0 to 2. So there's some area right in here, isn't there? And then there's some area on the other side. But look at what happens to this area, because this is an asymptote, isn't it? Keeps going down forever. So this area is actually infinite, isn't it? And on the other side, it's infinite going up. But it's okay, because we know already from what we did previously that we can have areas, regions that are infinite. But instead of infinite this way, do you see that these regions are infinite up and down? So let's see how we're going to attack the problem. What we do anytime we have our discontinuity is we first identify where it's discontinuous. So we have a discontinuity at x equals 1, which is in our interval. What if our integral went from 2 to 4? I wouldn't even care about this. I would just do it like a normal problem. So when you're on a test, you just have to be careful when you look at these integrals now. That function's discontinuity. I'm working on an interval that has that discontinuity in it. So it's something that you can, you have to kind of train yourself to look for, because you might miss it. And if you miss it, it'll be a wrong answer. All right, here we go. This is what we'll do. We will do an integral now. And, sometimes it helps to draw a number line. I like to do it this way. I want to go from 0 to 2, right? Where's my discontinuity? Happens to be right in the middle, which is great. That's fine. I'm not too concerned about that. Make sure my audio is recording. Yep. I hate to do this whole class and then not have audio today. So there's my 1 in the middle, right? What I will do is I will first do an integral that goes from 0 to 1. And next to that 1 on the top right, I'm going to put a little negative sign. What does a negative on the top right mean? Approaching it from the left. So really it's like the idea that first integral is going to be approaching this 1 from the left side on the number line. And then my function, let's go ahead and put it in here, 1 over x minus 1 dx. Whatever that area is, plus the other side. The other side of the discontinuity would go from where to where? From 1 to 2, right? But the 1 to 2, it would be 1 with a plus. That means I'd be on the right side of 1. Do y'all remember the little plus and minus from Cal 1? It was from limit notation, right? That's the way we called it left and right-handed limits. If you want to come in from the left, you do this. You want to come in from the right, you do this. So that's this, and then 1 over x minus 1 dx. So if you wanted to, you could say, look, this integral corresponds to this interval, and this integral here corresponds to this interval. So we're doing 2 separate pieces, right? Let's take a look at the first integral. This one right here. The antiderivative is natural log x minus 1. We're going to evaluate that from 0 to 1 from the left. Now we have to be careful here because we actually have the possibility of getting a negative in here. We're going to need to put the absolute value. Because we can't take the log of a negative number. So let's try this. Let's approach 1 from the left side. What happens? Just try plugging 1 in there. What's 1 minus 1? 0, right? 0? So if you do that, you get natural log of 0. I'm just going to write it underneath here. Natural log of 0. But natural log of 0 is what? Undefined, right? Remember what natural log looks like? This is what natural log looks like. So as you approach 0, what's happening? Where is it headed? Negative infinity, isn't it? So when I'm evaluating this, I need to kind of back up to make sure you really understand this. What does the one from the left tell you? That means you're plugging in values that are really close to 1, right? But on the left side of it. So someone give me an example of a value that would be really close to 1, but on the left side. 0.999, something like that, 0.999. If I plug 0.999 in here, what happens? 0.999, take away 1. I get a very small number and it's negative, but then takes its absolute value, it's positive again. So natural log of a very small number is really basically saying what's natural log of 0, and it's headed towards where? Negative infinity. So when we plug in negative 1, we get negative infinity. Are we done? Can we say diverges right now or no? Plus, now plug in 0. Plug in 0 here. 0 minus 1, negative 1. Absolute value, natural log of 1 is 0. So we get 0. This integral diverges. Because this part here goes to 0, this one goes to negative infinity. This diverges. Yes? Okay, let's go ahead and see what the other integral does. Plus, let me see here. Same antiderivative. One from the right to 2. So plug in 2 first. What do you get? 2 minus 1 is 1. Natural log of 1, so we get 0. minus, now plug in 1 from the right. So that means numbers that are just a little bigger than 1, so like 1.000001. Take 1 away from it, very small number. So it's still tiny. Natural log of a very tiny number is going where? Negative infinity still? It is plus, but all that's saying, see, this is the argument of the argument of the log function. It's going to 0, isn't it? When I plug 1 in, it's going to natural log of 0. The positive is just telling me what's happening right in here. The fact that when I do a number a little bigger than 1 and subtract 1, I'm going to get a very small positive number. Then I take the absolute value, it's still the same. Here, it was a very, very small negative number, but then I took the absolute value, so it didn't matter. In any case, both of them are headed towards natural log of 0, right? Whatever natural log is doing as I go to 0, so diving down to negative infinity. So we get here negative infinity, right? And we get over here positive infinity. Right? So you're probably sitting there going, well, wait a minute, hold on. I have negative infinity plus positive infinity, so it's like infinity minus infinity. Well, with these integrals, whenever you have a discontinuity on the inside and you split it into 2, if you get one of these to diverge, the whole thing diverges. So if any single one of those 2 integrals diverges, we're done. So I could have stopped here, but I wanted you to see the rest of it. Yes? Okay, negative infinity is coming from, look over here. If I said, what's the limit as x goes to 0 from the right of natural log x? So travel along the natural log function and let what's inside of it head to 0. That means let the x go to 0. Then the function starts to dive down towards negative infinity, right? So when I plug in 1 into this, I'm getting natural log of 0, which is basically saying what happens to natural log function as I go to 0. I go to negative infinity. And the same thing happens there. Does that help? This one, do you agree that if I plug in a number really close to 1, that goes to 0? But small negative numbers. That one also goes to 0, small positive numbers. Mm-hmm. For that side, slightly over 1, slightly under 1 here. The thing is, though, the absolute value makes it not matter. Because even though this is a very small negative number, absolute value makes it a small positive number. That one over there, it's a small positive number, absolute value, small positive number. So they're the same thing because of the absolute value. Let me do another example where that doesn't happen.
Because I'm looking at the bar you have up there, and if the value goes, the x value goes,
Yeah.
like if the x value goes this way, goes to in this direction here, he's going to increase it. I don't see it.
But we're approaching 0, not 1. See, 1, we're approaching 1 here, but then we're subtracting 1 from it, which means the inside of the log function. This is like our x. That's going to 0. So on our graph, we're approaching 0 from the right. Because the absolute value, though. Go ahead.
Never mind. Because I was saying, well, what if you make it a negative 2, 2 and then a subscript negative, would it still go to negative infinity?
No. If this was a 2,
Right.
then it would go to 2 minus 1, which is 1, which would mean it go to 0. But on that picture, see, the absolute value is what's making this whole thing kind of weird. If you'll allow me to, let me do another example, all right? And that way you can see how this will work out and how that plus and minus is actually going to matter. Is that all right with you? Okay. Yeah, that one will be good. So what was our answer for that? Sorry, I didn't put it down. It diverges.
Now, on this, you said if one diverges, both diverge.
If one diverges, you're done.
In this case, if we get one, we don't have to show the
You don't have to do the other one. Yep. That's because they're on different intervals. See, before, if you had infinity minus infinity, it's the single, yeah, you're talking about the integrand. It's all part of the same integral. This one, it was, different integrals separately, different a and b's. So if one of them goes to divergent, that's it. Let's try this. Integral from 0 to 2, 1 over square root of 4 minus x squared dx. Oh, you know what? Hold on. Go 0 to... I need this to work. Yeah, what did I have? 2? Yeah, we'll leave it there. We'll leave it there. So look at that integrand. Tell me where it's discontinuous. Tell me where you have a problem. At 2 or negative 2, right? If you try and plug 2 in for x or negative 2, you get division by 0. So when I look at this, my interval here, 0 to 2, the place that I have the discontinuity is at the end point, not in the middle, right? It's at the end point, which means I need to approach that 2 from this side, from the left side. I will not have to split this integral into 2 pieces because my discontinuity does not take place in the middle. So I don't have to come into it from one side and then leave from the other side. Does that make sense? So what I need to do is rewrite this integral, 0 to 2, and I'm going to just stress that I'm going to be coming in from the left side on that, of 1 over square root of 4 minus x squared dx. What's the antiderivative of 1 over 4 minus x squared? It should be a formula, right?
16 sine, dark sine, u over
What is it? X over 2. What else? Arc sine. What formula is this? 16? Everyone see it? Well, hold on. What's x over 2? Hold on. What formula was that? Oh, okay, someone's looking at the ones way down there. This is just arc sine of u over a, so x over 2. Evaluated from 0 to 2 from which side? Left side. Everyone okay with this being formula number 16? You could also have done that by doing trig substitution, but that's way more work. If the formula is there, do it, use it. All right, so let's try this. Let's plug in 2 from the left side. So what would happen if I just plug 2 in? 2 over 2 is 1. An arc sine of 1 we'll have to figure out, right? Yes? What happens if I plug 0 in? Get arc sine of 0? Let me just write down what we're getting when we try and plug in. 2 from the left, right, over 2. That's what I'm trying to do, right? Plug in 2 from the left. On the right side, arc sine of 0. Can we figure out these answers? How did I show you just a second ago to figure out your inverse trig? You could look at the trig function itself, sine. What is the domain? When we have the sine function, right, and its inverse, do y'all remember where the domain was cut off? Boy, this is like pre-cal, so a long time ago. For the sine function, we cut off the domain to be able to define an inverse. You have, I don't know how far back I want to go here to remind you. In order for a function to be a function, it has to pass the vertical line test, right? In order for it to have an inverse, it must pass the horizontal line test. This function sine as it sits is a function, but does not have an inverse. So what we do is we come in here and we cut it off, and we only define it between pardon me? That's where we define the sine function, just between there and there. Between there and there, negative pi over 2 and pi over 2, you get the entire range from negative 1 to 1, right? And you get the entire range in one interval. So that right there is a function, and it has an inverse because it passes both the vertical and horizontal line test. So looking at that picture right there, where would you get a 1 to come out? Because that's what's in here, right? 1 at pi over 2. Right? At pi over 2 is where 1 comes out. And then where would you get 0 to come out? At 0. So the inverse sine of 1 is pi over 2. And the inverse sine of 0 is 0. So your answer is pi over 2. Now, where does this negative come into play? Why is that negative important? Yeah, the number 2 right there, right? 2 with the negative sign means it's a little bit smaller than 2. And therefore, that over 2 is a little smaller than 1, isn't it? And you need that because look at this range right here. You want to get close to 1, but not bigger than 1, a little smaller than 1. You can't be bigger than 1, right? Sine can't be bigger than 1. So that's why you have to be on that side of it.
Would it be safe to solve this inverse trig function as what I did is like what we did earlier, where you set a 1 equal to sine, and then what sine equals 1 and cosine equals 1.
You can do that. That's where there's the give and take on it, you know. Because anyone can sit there and plug in 1 into the inverse trig function on a calculator. But to know where it comes from, I think is more valuable. So that's why I always show it this way, because I'm trying to get everyone to connect the pre-cal stuff to this. I would say at this point, do what you're comfortable with, but explore the graphs also and try and make it match. And
I did it with the unit circle.
You can do it that way too.
Yeah, that's how I did it.
Mhm.
That's what I'm talking about. It's like, where did sine equal 1?
That's fine. Unit circle's fine.
90 degrees.
We'll
Say I plugged it in there.
we'll have to see how the direction we come in from can play a part in this sometimes. So let me move to another example. Our answer is pi over 2 here. So this one converged, right? I think we'll do one more because I really want you to see an interesting behavior, something worthwhile here. How about integral 0 to 5 x over x minus 2 dx? We have our interval from 0 to 5. Do we have a discontinuity? At 2. Which means I'll need to approach it from the left, and then another integral will come in from the right. So two integrals, right? First integral will go from 0 to 2, left side of 2, x over x plus minus 2 dx. Then I'll go from 2, right side of 2, to 5, x over x minus 2 dx. Oh, I forgot a plus sign between those. That okay? That's just the setup. How about antiderivative? How are you going to find the antiderivative of x over x minus 2? Might require some work. Integral x over x minus 2 dx. How about u is equal to x minus 2? Du then would be dx, but then x is u minus 2, or plus 2, thank you. That's just solving this for x. So the new integral becomes on top, u plus 2, on the bottom, u, and then du. So this is just a basic substitution, right? U, and then it switches over, and then on that integral on the bottom, you can split it into 2. It's 1 plus 2 over u du. So the antiderivative of 1 plus 2 over u should be u plus 2 ln absolute value of u. I don't really need it though, because my interval, oh no, I am approaching 0, so let me just do natural log u plus c. So that's just the work for my integral, right? So let's come back over here now. Let's plug everything in. This integral should be u, which was x minus 2, plus 2 natural log of x minus 2, evaluated from where to where? 0 to 2 from the left. Plus the other one is the same thing, x minus 2 plus 2 natural log x minus 2, evaluated from 2 right to 5. Now this one's going to work exactly like the other one did because the absolute value on the natural log. Any questions though up to this point? Yes? Uh-huh. How'd I get the 2? The 2 what? Where'd I get this 2 from? Antiderivative. So antiderivative 1 is u. 2 over u is 2 times 1 over u. Antiderivative 1 over u is ln u.
Could we find the antiderivative first and then split up into the...
Oh, yeah.
We can do it that way.
Oh, yeah.
That'll be safe.
Oh, yeah. Yep. Okay, so let's plug in 2. Let's just try plugging in 2 right here into this, and let's see what we get. What's 2 minus 2? 0. And then what happens when you plug 2 in here? That's basically headed towards 0, right? It really doesn't matter, again, left or right, because I'm going to take the absolute value. Natural log of 0 heads to where? Negative infinity. So what will happen here is I will get negative infinity, and then let's just check. Minus, let's plug 0 in and see what we get. So plug your 0 in. 0, that's negative 2, 0, natural log of 2. So we get a number, don't we? Like this right here, 0 minus 2 is negative 2. 2 times natural log, plug in 0 there, you get negative 2, absolute value natural log of negative 2 is a number. So all that's just going to be a number, isn't it? I don't even care if it's positive or negative. If I have negative infinity and then a number, that's negative infinity. That diverges. We're done. I don't need to check the other integral. if any single one of those diverges, we're done. Okay? I have to show you one that converges. This is a little frustrating here. Let me see. Which one will converge? No. Mm-mm. Getting lucky. Yeah, pretty much. Okay, here we go. I've got one. I just thought of one that will work. How about this? Integral 0 to 2 of 1 over x minus 1 squared dx. So where's your discontinuity? At 1. Your interval goes from 0 to 2. Discontinuity is in here at 1. The antiderivative of this is negative 1 over x minus 1 to the first power, right? Okay, so this is the antiderivative of that. My new integral. I'm going to go from 0 to 1, 1 from the right, of negative 1 over x minus 1. Oh, shoot. Jeez. Hold on. Y'all want me to write it all down first, right, before I do the antiderivative? Okay, here it is split up. All right, split it at the discontinuity. Now, antiderivative I'm not going to show is negative 1 over x minus 1. Check it for yourself. I'm going to evaluate that from 0 to 1 from the left plus integral. Why do I keep doing integral? Negative 1 over x minus 1 evaluated from 1, right side of 1 to 2. Is that okay? Here's where coming in from the left and right makes a difference. Up to this point, it really hasn't. What happens on this first one if I try and plug 1 in here? Well, if I plug in 1, I get 1 minus 1 is 0. So I know that this is a fixed number over 0. I know this is getting infinite. It's just which one, positive or negative infinity. So if I plug in a number that's close to 1, right, close to 1 from the left side, those are things like 0.999, 0.9999. So if I take a number like that and plug it into the bottom left there, I get a negative on the bottom, don't I? So I know that the bottom is going to 0 through negative numbers. The numerator is positive. The numerator is negative, so negative over negative should be positive. So what happens when I plug in then 1 from the left side? It goes to infinity. Because what's happening here is you're getting negative 1 over something that's headed towards 0, but through negative numbers. Anytime you have a fixed number over 0, it goes to infinity or negative infinity. Pretty much, one or the other. It's just a question of which sign is it. Now plug 0 in. What do you get when you plug in 0? 1. But I can already stop here and say what? It's divergent. I said I wanted you to see where it made a difference which side you're on, which direction you're coming in from. You see what I'm saying? See, because if you came in from the other side on this one, from plus, this would have been negative infinity instead. Still would have diverged, but Just showing you that that matters because there wasn't an absolute value on it. All right, because of time and we've got to move on to the next section, I'm going to just end it with this, see how you do on the homework. I stopped at 22, right? See how you do with page 360, 23 through 31 odd. Then, of course, you can look at the evens if you want. All right, we are going to move to chapter 7. Chapter 7 is titled Applications of Antiderivatives, or Applications of Integration, or Applications of Integration. So we finally get to take everything we've done, all the techniques of integration, everything we've looked at, and actually apply it to stuff. So remember the basic idea behind the integral. It was a Riemann sum, right? We had the sum of all these rectangles, and we let it go to infinity, and we got the integral sign. We are going back to that now, as far as the geometric idea. If we wanted to find the area under a curve like this, we take this little rectangle in there, right? And we said that the width of the rectangle, right, our delta x, this little infinitesimally small rectangle, right, the width, that's our dx. And then the height of the rectangle is the function's value. And then the area of that rectangle is the height times the width, so f of x times dx. That went into the integral. And then the integral went from a to b, and that was our area, right? That I really hope you got that already. I mean, that's like hardwired, hopefully. So now what we're going to do is we want to find the area between two functions instead. So instead of having one function and find the area under it, let's take two functions and find the area between them. So take a look at this. That yellow part, and I will ask you on all these problems to graph the functions, to draw the rectangle, and to label this rectangle. So you're going to have drawings like this in all your problems. So get used to seeing this. I take one little sliver out of that area, one little rectangle, it looks like this. The width is still dx, but look at the height. Do you understand why it would be f of x minus g of x? It's the top, the blue function on top, however high that is, subtract however high g is, and that would give you the difference, right? The difference of those two. That's right. It's the one on top minus the one on bottom. That would give you your new height. So look at this. If you want to know the area of this, don't you just multiply that times this? The f of x minus g of x times this? So does it make sense that that would be the formula? I mean, that is your height times the dx, and the integral sign stays the same. Reasonable? All right, now we do have to take a couple of other things into consideration, though. What if your functions were below the x-axis? Yeah, what I'm saying is, like, what if you had, I'll do it right here. What if you had your axis like this, and you had a function that went like that, and then the other one maybe did this? Then which one would be? So is it the larger negative one? You see what I'm saying? Here's the way that I'm going to teach it to you because of what's going to come later. I want you to look at these problems this way. Like you are standing on the x-axis, right? I'll put you right here. See? That's you. Looking like I'm standing here. Let's say it's a flat sheet of paper is like the ground here. So we're looking from the top, right? I'm looking out that way, and in front of me I see the g function on the ground. I see the f function, right? I want you to look at it like the f is the one that's further away from you. Okay? The one that's further away is f, and the one that's closer to you is g. Does that make sense? So if now the functions are on the other side of me, below the x-axis, so now I'm looking down this way, I want you again to look at f as being the one that's further away from you and g to be closer. If you follow that, we should be okay the rest of the way. All right? If you wind up with a negative area at some point, just remember that you can't have a negative area. I mean, it would make sense to have negative area before. Remember, we get negative area whenever it was below the x-axis? Right? We would. So, I mean, we can still have negative areas now. But geometrically, area is always positive. So we might be off by a sign, but we're not going to let that affect us too much. Mm-hmm. The one further away from you. So in this case that I drew down here, the blue one down here would be our f, and this one would be our g. The one furthest away is f. You subtract the one closer from it. Trust me, this will help us where we're headed if we just have the same convention on all these problems. All right. Now, one thing I didn't point out that's important is that in the beginning, this integral, we always had a and b, didn't we? It was always given to us. But here, if you have two curves and I want to know the area between them, then figuring out a and b really means I need to figure out where these two functions intersect each other, don't I? And to find out where they intersect each other, to find a and b, you must set the functions equal to each other and solve. Right? If you want to know when two functions are the same, you have to set them equal to each other. So a and b will not be provided. You'll have to get it. Everyone understand geometrically what we're going to do? So here's our first example. Find the area bounded by 2x minus 1 and 7 minus x squared. Now here's where your graphing calculators come in. Here's where your knowledge of graphing comes in. The better you are at graphing, the easier this is going to be. But this is a line and a parabola. So I'm pretty sure, well, I know I should expect you could graph these, but maybe it's been a while. I don't know how comfortable you are with this stuff. So let's start off with a graph. Here are my x and y axis. How do I graph 2x minus 1? Go down 1, that's my y-intercept. From there I use the slope, up 2 over 1. And then I draw a straight line through that. This is f of x, and this is 2x minus 1. Agreed? How do you graph g? G is a parabola that is open down, goes up 7. So you could look at that function as negative x squared plus 7 instead of 7 minus x squared. So it's parabola opens down, move it up 7. So that's way up here somewhere. Comes down. And I'm not even going to be very accurate with it. I'm just going to draw it like this. Whoa. Okay, I'm trying to find the area of the region bounded by both of those. Where is it? Where's the area? Where is the area in question here? Above the red line and below the parabola. So right in here. Because eventually what happens down there? They hit each other and pinch off that area. So that area is somewhere in here. So my first drawing is okay, right? It's okay. Does everyone see, though, why it's not this yellow? Why isn't it that yellow? Because that region never gets closed off, right? And over there, it's not. So there's only one region which is bounded by both. and bounded, completely closed.
So isn't f of x mislabeled? So this is not further away?
That's going to, so we won't even really be thinking about f and g. We're just going to be thinking about who's further away, who's, all right? Top and bottom, basically. All right, here we go. What should we find? What do you want to do? We can find where they hit each other first, or we can set up the integral first. It really doesn't matter. You want to find the intersections? Okay, let's find the points where they intersect. So, you know, somewhere down there they hit, and somewhere up there. So intersections. So you have to set the two functions equal to each other. And that's a quadratic equation. So move everything over to one side. You can either factor this, or if it doesn't factor, what can you use? If it doesn't factor, ooh, you could do that if you wanted to. Quadratic formula, negative b plus or minus square root b squared minus 4ac, all that, right? So 2 and negative 4 are their intersection points. So that's on your x-axis. 2, and then back here, negative 4. I'm going to draw a rectangle in here to show me the typical slice. What does a typical rectangle in here look like? Let's do it now. Tell me about how high this is. How high is that rectangle? It's the top one minus the bottom one, right? So watch the way I write this. I think what I'll do is I'll put my rectangle down here. Like that. I'll highlight the rectangle so we kind of just know what I'm talking about there. I'm talking about this. The height of it is the top function, which in this case is 7 minus x squared, right? Minus the bottom function. What's the bottom function? 2x minus 1. Now, my use of parentheses is vital here, isn't it? I don't need the parentheses around the 7 minus x squared, but I do need it around the 2x minus 1. So this will result in what? 7 minus x squared minus 2x plus 1. Let's collect things together. Negative x squared minus 2x plus 8. Yeah? Now, how wide is this rectangle? Dx. Always dx. Just a little sliver. So we have everything. We have where the integral should start, where it should stop, and we have what the integrand looks like. So now we set it up.
Can I ask a-
Sure. No, you can ask.
All right, so we found the intersects.
Yes.
I was expecting that we would actually find a point. But
Well, we found the x value.
you just found the x-value.
Yep, because that's all you need on the integral. You only need to know where to start and stop. Your a and b are always x values, or they have always been x values. So all we need is the x. We don't need the y.
Wait, how did you determine your F and your G?
By looking at my rectangle and looking at how tall it is, it was the top one minus the bottom one. So the top one, the top of this rectangle is the green, right? And the bottom of the rectangle is the red. Everyone see that? Okay, so now my integral is going to look like this. I'm going to set it up right here. It's the integral from where to where? Negative 4 to 2 of minus 2x plus 8 dx. Now, could you integrate that? Yeah, negative 1/3 x to the third minus x squared plus 8x. From negative 4 to 2, you plug in, you get a numerical answer. I'm not going to do that. But that's it, right? I mean, we're set up. We're ready to go. On your next test, what you're going to find is that I'm going to, and some people don't like this idea. Some people that teach Cal 2 don't like this, but I like the idea. I ask you to draw me the picture, to show me the rectangle, label everything, set the integral up, and move on to the next problem. And then what I do is I have you take that home and do the computation. Because it's just kind of a waste of time for us right now to actually do that. All right? So this would be, on a test, this is where I'd ask you to stop for the in-class portion of the test. Set up the correct integral. Now, what I've done here is I did this problem with the aid of a graphing utility to make it nice and precise and pretty. So there it is right there. There's the graphs. There's my rectangle. There's my setup. And then, you know, here I already found the intersection. I didn't know how we were going to do this, but we found the intersection already. So we're done with that. Is that okay? All right. You like this better than partial fraction decomposition, trig substitution? Good. So now let's go and look at the possibility of having two functions that are not functions of x, but functions of y. I mean, we've always had functions that pass the vertical line test. They're functions of x. But hopefully you've seen somewhere in the past that you can have functions that go the other way, that pass the horizontal line test this way, but fail the vertical line test. So they are functions of y instead of x. Parabolas that open up sideways are examples of these. Those are two parabolas. Let's first, let me take this earpiece off for a second. Let's first take a look at this and just talk about why you could not do a vertical rectangle here. Why not just do what we did in the past? Look, if I have a rectangle right here, right, that's okay? I mean, I could figure out what the top and bottom functions are, right? The top one is the blue one, the bottom is the red. Yeah, but what about over here when I try and draw a rectangle to account for that sliver? What's the top function? The same as the bottom function. So if I try and subtract them, I get what? 0, which means that doesn't make sense. So you see that? So basically, anytime you have an area where the function on top comes around and becomes the function on bottom also, you can't draw your rectangles that way. Does that make sense or not? All right, so the thing is, we can't have that right there. We can have it here, that would be okay, but we can't have it at this place. So if we can't have it there, then what we need to do is look at it maybe sideways. Notice if you turn your head, you always have a top and a bottom, don't you? Always have a top and bottom? But that's going to change everything. If we're going to turn our head sideways and look at these as functions of y instead of x, then not only does our integral now have y's in it, we're also going to have to change the idea of a and b. Instead of being on the x-axis and going from a to b, we're now going to go on the y-axis from c to d. Why is c on the right side of d? Yeah, I'm going from small to big, right? A to B was always left to right, with small to big. When you're looking on the y-axis, small is on the right side, big is on the left side. Or small is down and large is up. Agreed? So the rectangle we have here, the width of it is dy instead of dx. The length of it is the function that comes out here, the f function minus the g function. So it's all the same thing, except in terms of y instead of x. See? Let's try an example to see if this makes sense or not. All right, find the area of the region bounded by x equals y squared minus 4y and x equals 2y minus y squared. I think my first question to you would be, what lets you know that these are functions of y instead of x? Well, act like you don't have the picture, because I gave you the picture. Look up there, right? What lets you know that these are functions of x functions of y instead of x? They're both solved for x, aren't they? Right now, if I give you a y, you can tell me what x is. It's usually the other way around, right? We usually write y equals and then something, and if I give you x, you give me y. This is backwards. So if you can solve your equations for x, they are now functions of y instead of x. Now, how are you going to graph these? Because you're going to have to. Anyone know how to graph something like that on their calculator? You turn your calculator sideways. You actually could do that, because it does turn out that basically having a function of x and function of y is basically the same thing. It's not 90 degrees, it's close to 90 degrees. If this is I'll draw it on the board. This is our x and y axis, right? Positive side, positive side. That's what xy looks like. So if I draw a graph here like this, if I try and switch x and y and make this y plus and this x plus, it's the same exact thing, but it's not turning it, I'm not twisting it. You have to get on the other side of the board. Who has a piece of blank paper? I can show it to you better this way. It's going to be sacrificial. It's going to be sacrificial. X plus y plus. Look at that right there. Okay? That's x plus, and this is y plus. Now, if I turn it, right, like this, switch x, y, then x is positive this way and y is positive this way. That's not the same as what we have here. The only way, this is what I'm trying to get to. The only way that this is the same if I switch x and y is if I actually come onto this side of the page, okay? I have to come over this side of the page and turn my head. If I turn my head that way, then what I'm seeing is this: y positive, x positive, which is the same as taking x positive, y positive, and switching x and y. So you could look at this as, you know what, just switch all your x's and y's. Make this problem a y equals x squared minus 4x, y equals 2x minus x squared, and then you could graph it on your calculator. You could, but that will hurt you in Cal 3, because in Cal 3 you have to be able to work with the variables as presented. You can't just switch x and y. So I want to take the rest of the last 10 minutes I have to just talk about how you can graph this on your calculator, because some people may not know how. So what I'd like for you to do is get your graphing calculators out. And what we're going to try and graph is, where is it? X equals y squared minus 4y. Now, here's the deal. Your calculator, normal calculator, when you're in the function mode, it sits there and it says y equals, and it wants you to graph, right? How many of you are okay graphing something if I give you like x squared? Everyone pretty much? Okay. But we can't do that. So you would have to solve this for y, which is just a friggin' disaster. So here's what we do instead. Go to your mode on your calculator, go to mode, and somewhere after you get to mode, you should have the option of function, parametric. It should say like func, para, polar, SEQ or something like that. Okay, select para. Now, this represents parametric equations instead of a function. Here's the way parametric works. Now go to your graphing. Okay, after you've selected parametric, go back to the graphing thing, and it should be asking for something like this. x1t, then it should say y1t, something like that. Anyone not have that? Everyone's okay? Here's what we're going to do. I'm trying to teach you a lot in a few minutes here. What this says is instead of giving me instead of saying, hey, look, tell me what y is in terms of x, parametric says, tell me what x is in terms of t, and then what y is in terms of t, which seems confusing right now. But what is it that we do know up there with the equation that's given? X is y squared plus blah, 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 or y squared minus 4y. We know what x is in terms of y, don't we? So what you start with here is if you know what x is up there, you start right here with the y and you say y is equal to t. Just put it in, y is t. Now you should have some calculators have the letter t. Other ones where your x variable used to be, it might say x comma t comma theta or something. Just hit that again, it'll put the t in. Everyone have t there? Now go back up to the x1. What's x1? Well, it's y squared, right? But what is y? T. So it's t squared minus 4 what? T. You see how this works? If y is t, then t squared minus 4t is really y squared minus 4y. And that's what x will be. Any questions? Now graph. It should give you a sideways parabola. However, your window may not be correct, or you know how back with functions you could adjust how much x you wanted to see? We can adjust how much t we want to see. So hit window and tell me what your t-min, go to your window and tell me what t-min and t-max are set at. 0 and 6.28. The standard default setting on calculators is 0 to 2 pi. For parametric plotting, it's 0 to 2 pi. So you're going to need to change that. I would change it -10 to +10, because that's basically going to give you a square window to look at, hopefully. -10 to 10. Sorry? Don't change any of your step size stuff. Graph it again. It may look exactly the same. Did you use the minus sign or the negative sign? Do it again. T-min is -10. T-max, positive. Let me see. Invalid dimension. Was it working before? It didn't work before? Well, something on your calculator is messed up. We'll have to do maybe a memory reset or something. Anyone anyone not getting it? The picture. Anyone not getting the sideways parabola? No? Everyone's good? Okay, get the other one then. You remember what the other one was? It was, don't erase the one you have. 2y minus y squared. So now you're going to be working with the x2t, y2t, right? The x2t, y2t. What do you let y2t be? T again. And then what do you let x2t be? 2t minus t squared. And graph. Yay or nay? Yes? Good? Huh? That's not going to tell you the answer. That's going to let you draw the picture. Well, I mean, some of them will, but now to find the intersection, you set them equal to each other. Now, since they're both solved for x, you can just set them equal to each other. Now you have a quadratic equation in y, and that'll give you your y values. Now, I'm going to finish this out later. I don't want to do any more of this, but this all I want to do here at the end was just show you how to use your calculator to graph things that are not technically functions. Now, check this out, because I think this is a pretty cool thing to know. Our whole life, we've been doing things like this, right? Let's just say that's the thing, and you type that in your calculator, and you graph it, right? You can stay in parametric mode and graph this. Here's how you would do it in parametric. This time, what is it that we know? And remember, this is y equals, right? Okay, so what is the variable that we are given? Like, the x is what we need to plug in to get y, right? So y will depend on x. X is kind of free to be what it wants. So x here, instead of y being t, x will be t, right? Let x be t, and then let y be what? T squared plus t plus 2. Do that on the third entry. For x3, y3, do t and then t squared plus t plus 2. And what you'll have is a standard parabola graphed the way your calculator always graphs. Right? You could graph the sine function. All you would do is t sine t. Make sense? We're going to study parametric equations later on in this class, towards the end. I can't believe I'm out of time. All right, homework-wise, I gave you that other section, homework. Area between curves. Okay, homework, page 369, numbers 1, 2, 5, 6, 7, 8. That'll get you started. Be ready next class, because we're going to finish this section up pretty quick, because we need to get through chapter 7. Pretty quick.